Hey everyone, welcome to The Explainer. Today, we're diving into a massive cornerstone of object-oriented programming in C++. We're going to demystify class inheritance, peek right under the hood at how memory is laid out, and really conquer the mechanics of compiled time binding. By the end of this, you'll know exactly how your compiler makes its decisions and why your data might literally get sliced away if you aren't paying close attention. Let's get into it.
All right, let's run through our agenda real quick so we know where we're headed. First, inheritance and class hierarchy. Second, compile time binding basics. Third, we hit the object slicing problem. Fourth, slicing in function calls. Fifth, base and derived pointers. And finally, number 6, our key rules and takeaways.
Okay, part 1, inheritance and class hierarchy. We're setting up classes A, B, and C. So we're establishing a classic is-A relationship here. We start off with a base class, class A, which has a simple integer variable a and a basic print function. Simple enough, right? Then we bring in class B, which publicly inherits from class A. Because B is an A, it gets all of A's properties for free, but it also adds its very own integer B. Now take a look at how the print function is handled in class B. It actually redefines print to output both the base data and its own new data, plus it introduces a totally new version of print that takes an integer parameter.
Now, before we go any further, I absolutely have to warn you about this because it's a huge exam trap. Overriding versus overloading. As we just saw, overriding is when you redefine an inherited function using the exact same signature, like B replacing A's print function with its own print function. Overloading, on the other hand, is when you create a brand new function with the same name but with entirely different parameters, like B bringing in a print function with an integer x. You really want to keep that distinction crystal clear in your head.
Just to wrap up our setup, let's introduce class C, which inherits from class B. We're essentially tracing a straight, linear is-a progression here. C is a B, and B is an A. Everything just cascades downwards. Class C gets its own variable, C, while inheriting absolutely everything from B, which, as we know, already inherited everything from A.
Moving on to Section 2. Compiled time binding basics. Let's understand static object execution. Here is our absolute baseline rule for compile time binding. The system calls functions on an object strictly according to the exact type of that object. Period. If you have a static object, the compiler makes up its mind about exactly which function to trigger before the code even runs. And this behavior, it cannot be changed on the fly. It is locked in.
Let's actually trace this in the code. In our main function, we're instantiating 3 static objects. We've got A1 of type A, B1 of type B, and C1 of type C. When we call A1.print, the compiler statically binds it directly to A's print function. Call B1.print, and it binds statically to B's overriding print function. And if we call B1.print with a 3, well, it binds to B's overloaded function. The compiler knows exactly what to do instantly because those object types are statically declared right there in the code.
And this is just a brilliant illustration of what's actually happening down in memory. Look at how the memory is allocated for that derived object C. It isn't just floating data, it's like a perfectly nested set of boxes. For C1, the base data where A equals 5 is packed securely inside the B block where B equals 6, and all of that is packed right inside the C block where C equals 7. Understanding this physical, nested memory layout is literally the key to surviving the major pitfall we're about to look at.
Which brings us to Section 3. The object slicing problem, losing the derived data.
Okay, read this crucial rule with me. When assigning a derived class object to a base class object, the system will only copy the data of the base class. The derived portion is completely discarded, tossed right in the trash. I can't stress this enough. Forgetting this exact mechanism is exactly where most compile time errors pop up on those tricky assignment questions. Let's play Visual Debugger for a second. Think about what happens when we execute the line A1 equals B1. Remember, A1 is an object of class A, so it only has physical room for the integer A. But B1 is an object of class B, so it's carrying both A and B. When you try to force B1 into A1, the compiler quite literally slices off the B portion of that memory block. The B equals 4 data gets tossed into a black hole, and A1 is left sitting there with only the A equals 3 part. Because of this brutal slicing action, it is so easy to fall into classic exam traps. Like, if you try to call A1.funB after that assignment, it completely fails with a compile time error.
Why? Because A1 is strictly statically bound to class A, and class A knows absolutely nothing about fun B. It's totally oblivious. Calling the overloaded A1.print with a 3 fails for the exact same reason. That function belonged to the sliced-off B class. And hey, if you try A1 equals C1, that is a double slice. Both the B and C memory portions are just entirely wiped out.
All right, section 4, slicing in function calls, the hidden pass-by value risk.
So how does this sneak up on you? Let's break down exactly how passing an object by value triggers slicing without you ever even writing an equal sign. First, you define a function that takes a base object by value, something like void fun, taking parameter A. Second, you pass a derived object, like C1, right into that function parameter. Now, because the function specifically carved out memory for an A object, the C object you passed in is implicitly and completely silently sliced down to the base class just so it can fit into that parameter slot.
See, when we call fun with C1, the parameter is AA. Think back to our nested C object block. Those C equals 7 and B equals 6 sections, aggressively chopped off. Only A equals 5 actually makes it inside the function. If you try to call a print function inside fun, it's only going to print A equals 5 and it will strictly use class A's compile time-bound print method. Your derived data is just completely gone.
Moving on to section 5, base and derived pointers, hiding the truth in memory.
Now here are the strict rules for pointers that you really need to cement in your mental model. Yes, base pointers can absolutely point to derived class objects, but base pointers basically wear blinders. They can only see base class members. But here is the fascinating part. The derived parts aren't actually destroyed or sliced this time. They still exist perfectly intact right there in memory. They're just completely hidden from the pointer. And because of static compile time binding, the system is only going to call the base class functions, totally ignoring any derived overrides you might have written. Let's look at this assignment. A pointer A2 equals new B with 3 and 4. We are pointing an A-type pointer at a brand new B object in memory. But because it is an A pointer, if we call A2 arrow print, the system just blindly triggers class A's print function, even though a perfectly good B override is sitting right there. And if you try to call A2 arrow fun B, you get a compile time error. The data is there in memory, but compile time binding strictly refuses to look past the base class definition. It is the ultimate classic pointer trap.
Finally, section 6, key rules and takeaways, your compile time binding cheat sheet. Okay, here is your ultimate cheat sheet. This condenses everything we've talked about into reliable programming patterns. First, for static objects, binding is to the exact object type and it simply cannot change. Second, when you assign a derived object to a base object, it physically slices down, discarding data and throwing errors on derived function calls. Third, pass-by value implicitly slices your objects in that exact same way. And lastly, base pointers can point to derived memory, but because they're statically bound to the base class, they just hide the derived data and only ever call base functions.
All of this leaves us with one massive lingering question. If base pointers obstinately refuse to call our beautifully overridden derived functions because of compile time binding, how do we force them to actually see the truth in memory? Well, the hint is virtual functions. But that kind of dynamic runtime magic is a topic for our next explainer. Keep this question in mind, definitely keep practicing these memory boundaries, and I'll catch you next time.